Section 2.6, limits of infinity, horizontal asymptotes. All right, so previously we talked about infinite limits, we called them. Limit as x approaches a of f of x equals either positive or negative infinity. And we use that to actually define the existence of a vertical asymptote. All right, so we call those infinite limits. And so the graph is, either shooting off to infinity or negative infinity as x approached a number. Right, so we had our vertical asymptotes there. So here we want to look at what we're going to call limits of infinity, or limits at infinity. It might be a better way to say it, keep them straight. So infinite limits where the limit as x approaches a is equal to infinity, positive or negative. And then here we're looking at limits of infinity, or limits at infinity, where we look at the limit as x approaches infinity and what happens to the value of our function. All right, so for example, take our function f of x equals 2x squared minus 3 over x squared plus 3. We just do a little table of values just to give us an observation about what's happening to the value of that function. As in this case, notice our x values are getting larger. Right? So when 0, 10, 100, 1,000, both positive and negative. So as x approaches infinity, positive, x approaches infinity, negative. Right? But in either way, as x gets infinitely large, whether it's positive or negative, we do have the function values approaching 2, right, according to our table. And if you graph the function, this is the graph that you see. It's going to look something like this. Right? Yeah, so then in terms of our limit statement, right, so I've got the limit as x approaches infinity equals 2, limit as x approaches negative infinity equals negative 2. Right? So this leads us to our definition of this limits of infinity, or limit at infinity. We let f be a function defined on some interval, say from a to infinity. Then the limit as x approaches infinity of f of x equals L means that the value of f of x can be made arbitrarily close to L by taking x sufficiently large. And that's kind of similar to the limit definition that we started out with. Remember that whole making f of x arbitrarily close to L by taking x sufficiently close to a. Well, in this case, since x is approaching infinity, we say that we're making x sufficiently large, but the idea is still the same. And of course, there's going to be a similar definition for the limit as x approaches negative infinity, just in the opposite direction. But basically what you're looking at is, you think of this in terms of end behavior. Remember from algebra, you talk about the end behavior of a function. We talk a lot about end behaviors of polynomial functions, whether it shoots off to infinity or negative infinity, that kind of thing. So that's what you're looking at here. As x approaches infinity, as x approaches negative infinity, what's happening to the value of the function? Is the value of the function approaching some number? Right? Is there a limit as we plug in larger and larger values for x? For example, now I want to talk about this in a couple of different ways. So here's the limit as x approaches infinity of e to the opposite of x plus 3. And, set up a table of values here. And really, I mean, you talk about x approaching infinity, but look at the values of x that we plugged in here. We didn't have to get very large. I mean, 100 is not that big of a number in the context of infinite. But we didn't have to get very large in order to start to see the pattern, or that the function values were getting closer and closer to 3. Right? And again, the idea, I could plug in larger and larger numbers, but it's not going to change my observation. I mean, I can see what's happening already. So infinite is, be careful with that term. I'm going to talk a lot more about infinity as we go through with this, but just be careful with that concept of infinity. Remember, infinity is not a number. It's a concept. It's describing unboundedness. So when we say approaching positive infinity, that means that the values are just getting larger and larger positive. Approaching negative infinity, right? They're getting larger and larger negative, but we never treat infinity as a number. Be careful there. And also, I mean, you can look at the graph of this function. It's a basic exponential function, but that's the graph of it. And you can see, remember, we talked about exponential functions. I did that little review. And we know that every exponential function has a horizontal asymptote, because the graph of every exponential function is either going to look like the one that we have here, or is going to do this. Right? I mean, every exponential function has the same behavior, so they all have horizontal asymptotes. In this case, it just happens to be at 3. But in terms of the limit, so limit is x plus infinity of e to the opposite of x plus 3 equals 3. Now I want to look at that another way, without the table. Because I will always tell you the table is kind of the method of last resort. I mean, if I have no other way that I can make an observation or determine what the limit is, then I put together a table of values to see what happens. Right? But we would prefer to be able to do that using some other basic processes. So if I look at this, limit is x approaches infinity, e to the opposite of x plus 3. The first thing I did was use our limit laws just to break this up and say the limit of a sum is equal to the sum of the limits. Now be careful with the limit laws. I mean, I keep preaching to you about not reading more into what these definitions and theorems say than what they say. You never assume or presume. It has to be clearly stated. Right, and remember we talked about the limit laws. All those limit laws were requiring that the limits actually exist. So when we say the limit of a sum is equal to the sum of the limits, that is true provided that the limits actually exist. I'm going to talk more about that later in this section, so don't keep that in mind. Now, the first one that I'm interested in is that limit as x approaches infinity of e to the opposite of x. And this is just, again, basic algebra, e to a negative, or remember, e is a number. And if I take that and raise it to a negative power, and I can rewrite it as 1 over e to the positive. Now, in this case, like I said, I'm not looking at x as being negative. All right? But the fact that that's e to the opposite of x, that would be equivalent to 1 over e to the x, right? We can change the sign on the exponent. That's the more basic application of that rule of exponents, right? So if you move a factor between the numerator and denominator of the fraction, it changes the sign of the exponent. So I can then look at this limit as x approaches infinity of 1 over e to the x. Now the limit as x approaches infinity of 3, that's our limit of a constant. That doesn't change from the limit laws that we had previously. The limit of a constant is still a constant, right? So that's done, so that's 3. But then this is the other, we talked about this I think in a previous section. If I look at e to the x, as x approaches infinity, all right, as x approaches infinity, oops, wrong choice, then e to the x is approaching infinity, all right? So as x approaches infinity, e to the x of course is approaching infinity, because e is approximately 2.72. You raise that to larger and larger powers, it's going to get larger and larger and larger. But this is one of the things we had mentioned earlier. If I have a fraction whose numerator is a constant, in this case it's 1, and the denominator is just getting larger and larger and larger, you take that constant divided by larger powers, we said the value of the fraction is going to continue to decrease. So if I have a denominator that's getting larger with a numerator that's constant, then the value of that fraction is going to get closer and closer to 0. And that's something to keep in mind, because we use that a lot. That's a good observation when you're talking about these limits of infinity. All right, so as we're plugging in larger and larger values into a denominator, if the denominator gets larger, then the fraction is going to approach 0. Just the opposite is true. What if I plug in values and the denominator gets smaller? If the denominator approaches 0, then the fraction is going to approach infinity, right? Because you take a constant divided by smaller and smaller values, the value of that fraction, that quotient, is going to get larger and larger and larger. So there's some kind of an opposite, or we call it an inverse relationship. If the numerator remains fixed, so keep this in mind for future reference. If the numerator is a constant, if the denominator gets larger, the fraction gets smaller. If the denominator gets smaller, the fraction gets larger. Right, it's just an inverse relationship. So that's pointing that out. This it's not just having to use table of values here, but we can do this using some of the things we're already familiar with. So I do have a function, a limit that is approaching 3 in this case. Graphical examples, right? So these limits of infinity, or limits as x approaches infinity of f of x, being equal to a constant. And you can get some different things graphically that happen with these functions, because remember, we said this is looking at the end behavior of a function. All right? It's not just about, or it's not about the entire function, it's only what's happening as those x values get larger, whether they're positive or negative. So graphically, you can have something like this happening, like we had in that previous example, where the function is approaching some number, right? You could also have something like the second one, where again, notice, it's crossing over that asymptote, but eventually, as x approaches infinity, the graph starts approaching that asymptote. And then something like the third one. I mean, these are kind of rare, but it is a possibility. Notice, the graph, the function values are oscillating. They're going, positive, negative, but they are getting closer and closer still to that horizontal line, to that asymptote. So even though the values are oscillating and they're moving, on either side of that horizontal line, they are still closing in or getting closer and closer to that line. And that's the idea of a limit. Remember, that's what a limit describes. I'm able to say that even though it's not doing something like this one, it's just directly approaching the line, it's still getting closer and closer to the line, even though it's revolving around the line or oscillating around that line. And that's what a limit does. It's describing the fact that the function values are getting closer and closer to some number. But again, those are rare, but you will actually see something like that pop up on occasion. Now that's just the negative infinity idea, right? So that's the same idea as the limit of infinity. Here's our limit as x approaches negative infinity, right? So there's no difference there, just approaching negative infinity. Now here's our definition that we ultimately then use for the horizontal asymptote. So just like we had with the vertical asymptote, remember, the limit as x approaches a of f of x equals infinity, where the graph is shooting off to infinity or negative infinity, we define that as the existence of a vertical asymptote. Here we've got the existence of our horizontal asymptote. Now the line y equals L is a horizontal asymptote of the curve y equal f of x if either the limit as x approaches infinity of f of x equals L, or the limit as f of x as x approaches negative infinity equals L. All right, now remember, vertical asymptote's equation, x equals that a value, whatever that value was. And for a horizontal asymptote, remember those are horizontal lines, so the equation is y equals. And in this case, y equals whatever that limit happens to be. Right. Now, when you talk vertical and horizontal asymptotes, and here's just again a quick algebra review, remember you can have an unlimited number of vertical asymptotes. I mean, just however many points at which you have that behavior, that you can have any number of vertical asymptotes. You can only at most have two horizontal asymptotes. There can only be one on the left and one on the right. And with most functions, unless it happens to be a piecewise function, I'd say with most functions there's usually only one. Now it doesn't necessarily have to be the same on both sides. I mean, if you go back up here and you look, I said the first example that I gave you, really all of them, there's a horizontal asymptote only on one side of each of those graphs or those functions. Right? So you could have a horizontal asymptote that's on one side or both sides. They don't necessarily have to be the same, although that's usually the case with most functions. I said usually it's a piecewise function or something like that, where maybe you end up with a different definition going off to the left and off to the right, and you could have multiple horizontal asymptotes. All right, so for example, and this one I'm just taking from the examples in the book, finding, and of course watch your language here, the terminology. So we're looking for infinite limits, we're looking for limits of infinity, or like I said, that's what I also call limits at infinity. That might help to keep those straight. And then we're also looking at identifying the asymptotes on the graph of the function. And we're using the limits, right, to justify or define the existence of the asymptote. So don't just, oh yeah, but there's a vertical asymptote here and a horizontal asymptote there, I see it. But no, you need a definition. Why? Prove it, justify it. And that's done using the limits. So for the infinite limits, all right, that's the one where the function is shooting off to infinity or negative infinity. So I'm looking at my graph, and visually you can see where these are located. I mean, I've got a vertical asymptote here at -1. I've got a vertical asymptote here at 2. So now I just want to describe those using our limits. So what is the behavior here with respect to that vertical asymptote? Well, I've got the limit as x approaches -1 of f of x equals infinity. And it's the same behavior from both sides. Right? So as we approach -1 from the left, as we approach -1 from the right, in either case, we're shooting off to infinity. There's our appropriate limit statement. Now for 2, we've got different behaviors here and here. Now when we define the vertical asymptotes, we said, it doesn't have to be the same behavior on both sides. You don't even have to have the behavior on both sides, right? As long as either the limit as x approaches a, the limit as x approaches a from the left, or the limit as x approaches a from the right, if any one of those is infinity or negative infinity, then you have a vertical asymptote. Right? So it doesn't have to be the same. You don't even have to have that behavior on both sides. That's a misconception, I think, sometimes with this as well. We think it has to be the same, or we think that it has to have this, some type of behavior on both sides of the asymptote. No, it only has to happen on one side. But in this case, I can use either one of these statements. You don't have to necessarily do both, but I can use either one of these statements to justify the existence of that vertical asymptote. So here's an infinite limit, but it's a one-sided limit. The limit as x approaches 2 from the left is negative infinity. And then the limit as x approaches 2 from the right is positive infinity. All right, so each of those are infinite limits in their own right. Now the limit, remember, as x approaches 2 in this case, does not exist, period. Right? But we're able to describe the left and right hand limits as being infinite limits. Now also remember too, a lot of reminding you, these limits excuse me, these limits still do not exist. Right? We said a limit that's approaching infinity is a limit that does not exist, because the value of the function is not approaching a specific number. But we are able to describe the behavior of the function by saying that the function value approaches infinity or negative infinity. Okay, so be careful again. It's just don't misinterpret the language or the terminology that we're using to be clear on what we are actually describing here. All right, so those are all infinite limits, but technically none of those limits exist. Now the limits of infinity, or the limits at infinity, I tell you there's always only going to be 2 of those. All right, in this case, because of the graph, I do have 2 different behaviors, but those are your horizontal asymptotes. That's what's happening on the left side, it's what's happening on the right side, in that as x approaches infinity, I did the right one first, as x approaches infinity, excuse me, we have our function value that's getting closer to that horizontal line, which is at 4. And then as x approaches negative infinity, so there's our positive infinity, and then as x approaches negative infinity off to the left, again we do have our function that's approaching a horizontal line, and that one is located at 2. So then in terms of our asymptotes, each of those infinite limits on the right gave us vertical asymptotes. So we do have a vertical asymptote whose equation is x equals -1 and x equals 2. Remember, all those need to be given as equations of lines because that's what they are, vertical lines. X equals, horizontal lines, y equals. So then our horizontal asymptotes that we got from the ones on the left, approaching 2 and approaching 4. So y equals 2 and y equals 4. All right, so any question like that, yeah, you justify the existence of the asymptote using a limit, either an infinite limit or a limit of infinity, and then you give the equation of the vertical and the horizontal asymptotes accordingly. This next little observation is going to be a pretty important little tool for us. It's going to be another tool to put in the toolbox that we can use in the context of other types of problems. So this is one to make a special note of and remember. Look at the function f of x equals 1 over x. The graph of that function, that's the graph that I have over here. That's basically what the graph of that function looks like. And you can graph it on your calculator if you wish. I'm interested in the limits of infinity with that function. Look at the limit as x approaches infinity of 1 over x. All right, as we approach infinity, that function is approaching the x-axis. All right, so the function value is approaching 0. Same thing happens on the left side. If x approaches negative infinity, all right, then again, the function is approaching the x-axis. All right, it's approaching the horizontal line y equals 0. So that function has a horizontal asymptote, which is the x-axis. More importantly, I would say that the limit exists, and in both cases, the function is approaching 0 as x approaches infinity or negative infinity. Look at the function f of x equals 1 over x squared. I'm going to sketch that one in as well. And again, you can graph these if you wish. See nice pretty pictures. But if you graph 1 over x squared, you're going to get a graph that looks like this. It's going to have the same basic shape to the right side, but the left side gets flipped up because the x squared makes everything positive. But that's the basic shape of 1 over x squared. Notice I get the same behavior there. As x approaches infinity, as x approaches negative infinity, in both cases, just like with the previous, the graph is approaching the x-axis. The function is approaching 0. If you look at the graph of 1 over x cubed, guess what the graph of 1 over x cubed looks like? Looks just like that one. It just gets closer to the axes a lot quicker. You look at the graph of 1 over x to the 4th, guess what it looks like? It looks like that one. It just again gets closer to the axes a lot quicker. And so any odd degree that you put on that x, so 1 over x to the 5th, looks like that. 1 over x to the 6th looks like that. The even degrees versus the odd degrees. All right, so you have these two basic shapes to these functions, but notice again, they're all of the same form. They're all of the form 1 over x to a constant. The graphs are going to take on one of those two forms. But in either case, regardless, the value of the function is always approaching 0 as x approaches infinity. That's a pretty interesting observation. It's a good observation. So that leads us to this next little theorem that says, given a positive value for r, and we're looking at r as a rational number. Now, again, review, what is a rational number? That's a fancy word for a fraction. So what does this mean? As long as I restrict the r value to be a positive fraction. Right, now that also includes integers. Okay? So in other words, any positive value. Then the limit, as x approaches infinity, of 1 over x to the r is always going to equal 0. I don't care what the value of r is. And the limit as x approaches negative infinity of 1 over x to the r will also equal 0. Again, I don't care what r is, as long as it's a positive value. Now, we also have, provided that x to the r is defined for all x. Now, that kind of brings in, complex numbers. So let's say r happens to be 1/2, right? Square root. Then x can't be negative, right? Because that would give us an imaginary number. Right, so we have to keep ourselves within the real number system. We have to have defined values. So as long as all that, we actually have values that exist within the real number system, then the limit as x approaches infinity, the limit as x approaches negative infinity of 1 over x to a positive power is always going to equal 0. And that goes back to what we had said earlier when we looked at those examples. Remember I said if the numerator was fixed and the denominator was getting larger, right, then the value of the fraction is always going to get smaller and it's always going to approach 0. Right? So that's going to be an important tool to us. And I'll show you a couple of examples with that and how we're going to make use of something like that. So for example, let's find the limit as x approaches infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. All right, so as x gets larger, notice, of course, the numerator is going to get larger, the denominator is going to get larger. Now back to our discussion on that relationship, we've already said if the denominator gets larger, the fraction is going to go to 0. But that's only true as long as the numerator stays fixed. That's not happening here. The numerator is also getting larger, So the fact that the numerator is approaching infinity, x approaching infinity makes that numerator larger, means this is approaching infinity. It also means this is approaching infinity. Now the numerator approaching infinity, that wants to make the fraction larger. The denominator approaching infinity, we already said, wants to make the fraction smaller. So there's a tug of war going on here, right? As far as what the value of the fraction itself overall is doing. Now that's again going to be another discussion for a little bit later. What happens if I have an infinity over infinity? Okay, and which one wins the tug of war? Excuse me. All right. So here's a tool that we're going to make use of. We've talked about using some different techniques to rewrite our functions previously to get them into a form that we can actually evaluate the limit. So this is kind of along those lines, and it's going to be setting this fraction up to make use of this theorem that we just talked about. That one that says the limit as x approaches infinity, positive or negative, of 1 over x to a positive power will always equal 0. So what I'm doing is I'm taking this limit as x approaches infinity of that fraction and using a little bit of algebra. Now there's a couple of things, I want to talk about this a couple different ways. First of all, notice all I'm doing is I'm dividing every term in the numerator and the denominator by the highest power of x in the denominator. Right? It's one of those cases where the ends justify the means kind of thing. It's like, well, why? Why do you do that? Well, it's to see what happens if we do, and then how we're able to actually evaluate this thing. Now, technically what's happening, here's the basic algebra. Remember, when you talk about an equivalent fraction, how do I get an equivalent fraction? I can take any fraction, and as long as I multiply the numerator and denominator by the same thing, then I have an equivalent fraction, right? I don't care what you multiply by, as long as you multiply the numerator and denominator by the same value, then you get an equivalent fraction. So that's the basic process in play here. We use this a lot. We do this all the time. That's actually what some of the stuff we were doing earlier, right? Like when we multiply by conjugates and that kind of thing. So this is a trick that we use all the time when we're working with fractions to rewrite them into equivalent forms that we can actually then work with, right, to do whatever it is that we need to do. The trick is, of course, to multiply by the appropriate expression or number to get it into a form that we can use. So here, the reason we're dividing by the highest degree of the variable in the denominator, let me emphasize that, is because it guarantees you that you're going to end up with a non-zero constant down here. Because if I divide by the highest degree of the variable and the denominator, then whatever term it is that contains that highest degree, you're going to be dividing out the variable, and you're always going to be left with a non-zero constant. And that's important because, remember, if our denominator is 0, we have an undefined fraction, we have a limit that does not exist. But if my denominator is not 0, then I can always evaluate the limit. Okay? So there's a reason why we're dividing by what we're dividing by. So there's two things in play there: basic algebra with fractions, equivalent fractions, and then why we're choosing what we're choosing. All right, so we're always dividing both numerator and denominator by the highest degree of the variable in the denominator. All right, so that's what I have set up over here. And then we just simplify each one of those. So now I've got 3 minus 1 over x minus 2 over x squared, 5 plus 4 over x plus 1 over x squared. And then I went ahead and rewrote this using our limit laws, because notice now the next step, what I'm doing is I'm setting this up to use that theorem that we just mentioned with the limit as x approaches infinity of 1 over x to the r. All right, so I took the limit of a sum and difference and I broke them up into the individual terms. I also pulled out constants. But notice then each one of these is now going to give me a value of 0, because each one of these is limit as x approaches infinity of 1 over x to a power. And so each one of those limits, that's the theorem, that's why it's so useful, each one of those has a value of 0. Now the other two I have, the limit as x approaches infinity of 3, limit as x approaches infinity of 5, those are both limits of constants, right, which give us the constants. Now I'm asking at this point that you practice writing it out this way. Certainly we loosen up and we kind of, I'm not going to have you go through and rewrite all this and waste your time writing that out when I can make the same observation right here. Okay? But for now, I would practice writing that out so you understand and remember why exactly you're getting the values that you're getting. So why is this 0? Why is that 0? Why is that 0? Why is that 0? It's because of this particular theorem, that limit as x approaches infinity of 1 over x to a power. Okay, so again, It may seem a little redundant and like writing it out multiple times, but it is a little tool. It's a process we're going to use a lot, so I want to make sure that we're clear on exactly what's happening here and why it works the way that it works. Right, but once we have it in that form, so like we said, that's always the objective. Can I get the function or the expression written into a form where I can then actually evaluate the limit? Well, now we can do that. So each one of those is 0. Each one of the other constants is a constant. So then I've got 3 minus 0 minus 0 over 5 plus 0 plus 0, which leaves us with 3/5. And so that would be the value of that limit as x approaches infinity. And since that is the value of our limit of infinity, then what does that tell me graphically? That tells me that this function has a horizontal asymptote whose equation would be y equals 3/5. And if you remember from algebra, you may or may not remember, but when you're dealing with rational functions and you remember you would compare the degree of the numerator with the degree of the denominator. And if the numerator and denominator had the same degree, then that was your horizontal asymptote. So there's kind of an algebraic tool at work here, but that only works if it's a rational function, right? So what do we do with functions that are not rational? Well, that's where this limit definition is coming into play. It allows us to deal with a lot more situations. I included another example just to, again, show you how with proper manipulation or recognition of the function, you can apply some of these basic processes. So I've got limit as x approaches infinity of x plus 2 over the square root of 9x squared plus 1. All right, it's a rational function. Now I've thrown in an extra, that square root thing. So here, and here's where you got to be careful. If we look at, the highest power of the variable in the denominator, it's not x squared. Even though, wait, there's a big x squared sitting right there, but no, that x squared is under a square root. So when we talk about dividing the numerator and denominator by the highest degree of the variable, you've got to be careful of something like that. Now we're taking this, and this is very loose, the square root of x squared equals x. That's provided that x is positive. And there are limitations to that statement. I could go off on a tangent and say, well, actually it's the absolute value of x and all this, but for our purposes, okay, we'll take the square root of x squared to be x, but don't tell that to anybody and tell them that I told you that, because no, that's not technically true, but we're using that for our purposes. Anyway, like I said, I can get off on a tangent on that. My point being, because that x squared is under the square root, the highest degree of the variable is not x squared. The highest degree of the variable is actually x, because when you pull that x squared out of the square root, right, it's x. So I'm dividing the numerator by x, notice, x over x plus 2 over x. I'm still dividing in the denominator by x squared, but it's under the radical. And because it's under the radical, that square root of x squared is actually x. All right, so that, just a little bit different little twist, a different look at these different things that pop up in these different functions and how we can tweak the process, right? It's the same basic concept. We just may have to tweak things, be a little bit careful in how we apply them. But from that point forward, it's pretty much the same as previous, right? So now I've got that limit as x approaches infinity. I simplify each of the fractions. I've got 1 plus 2 over x, square root of 9 plus 1 over x squared. Remember, we do have a limit law that says the limit of a square root or the limit of a radical is equal to the radical of the limits. So all of this is still based upon limit laws. We also have the limit of a sum as the sum of the limits. So all of this rewriting in the next step, that's the sum of the limits. This is the limit of a radical. Actually, it all started with the limit of a quotient, right? It's a quotient of a limit. So there's a bunch of limit laws in play right there. But then each of those, again, is set up to use that theorem. And that now each of those where I have a limit as x approaches infinity of 1 over x to a power, each one of those has a value of 0. And the others are both limits of constants. So the limit of a constant is the constant. So I've got 1 plus 0 over the square root of 9 plus 0, or 1 over the square root of 9, or 1/3. Okay. So same process, same idea, it's just a different, it's a little bit of a tweak. to the problem, just to show you a different little variation on the situation. Sketching graphs from time to time in your homework assignments, they'll ask you to sketch graphs that kind of fit or illustrate the concepts or the situations that we've been describing. So here's one where we're sketching the graph of a function f for which each of the following is true. Now, when you're asked to sketch the graph of a function, typically there's an infinite number of ways that you can draw the different functions that fit the requirements. So as long as you're meeting the requirements that are stated, there are different variations certainly that you can make with the graphs of the functions themselves. So not everybody draws the same graph. There's typically kind of like a basic graph that most of us would draw, but you can get creative with these if you wish, but just as long as you're keeping track of the main components. So here we're looking at drawing a graph that that illustrates these infinite limits and limits of infinity. What I would do with these type of things is first of all recognize the asymptotes. Because anytime you have asymptotes on a graph and you can draw those asymptotes in, then that usually makes it a lot easier to draw the graph itself. So we want to recognize that, again, if I have an infinite limit, limit as x approaches a equals infinity, like we do here and here, then I'm recognizing that there are vertical asymptotes there at x equals 0, and again at x equals 0. Now this one coming from the left and from the right, so we have to deal with the one-sided aspect of that, but at least I know there's a vertical asymptote at 0, which is the y-axis. And then the other two, right, our limits of infinity, where x approaches infinity, x approaches negative infinity, we know those give us the existence of horizontal asymptotes. And again, it's the same in this case. Limit is 1 here, limit is 1 there. But the main observation is as x approaches infinity, x approaches negative infinity, there's a horizontal asymptote at 1. So we can draw that in. Horizontal asymptote, y equals 1, vertical asymptote, x equals 0, and then worry about the individual limits and making sure the graph illustrates those. And I always just go like from left to right. So I would start with, okay, what happens as x approaches negative infinity? Because that's the left side of your graph. I know that my function needs to approach 1, so I just drew in this little piece of the graph that approaches 1. Now, it doesn't mean I can't draw this. That also approaches that line. That's fine. You could draw it either way. That's what I mean. There's a lot of different ways you could draw these graphs. The next thing I run into is my vertical asymptote at 0, which we know as x approaches 0 from the left, we have to shoot off to infinity, so we know we have to do that. But what do I do if, instead of drawing the first one, I drew this? Well, that's fine, because I can always just do that, right? Remember, the behavior here at the end behavior, I don't care what happens in the rest of the graph, as long as we approach negative infinity, we start approaching that horizontal line. Same thing is true with the vertical asymptote. I don't care what happens between here and here. It can dance around, do whatever you want, as long as it's a function. I may not get too carried away there. So maybe we can do all kind of stuff right here. Doesn't matter. As long as eventually, right, it approaches the vertical asymptote. Okay, so there's always kind of like a basic graph you can draw, but then, if you get tired of drawing basic graphs, you can always draw a few little extra things in there, as long as you meet the requirements that are specified. So that's the limit as x approaches 0 from the left. Then we hop over and we got the limit as x approaches 0 from the right. Okay, so then the same thing, as approach 0 from the right, we're approaching negative infinity. So that's why I went ahead and did that. As we're approaching 0 from the right, the graph has to go down. And then lastly, we have x approaching infinity. And again, we're approaching that horizontal line, y equals 1. So again, I know that has to do this. And then I just connected the pieces. Okay. So you're going to see that pop up from time to time in the homework where they're asking you to illustrate graphs, to illustrate the different concepts using a graph. There's not always one graph. There's kind of a basic graph, but you can do a lot of different variations on those things. But I always just kind of look for the vertical and horizontal asymptote thing. If there's any specific points that are identified, go ahead and plot those points. And then just move from left to right along your graph. You say, okay, let's start with negative infinity. What happens there? Do I run into any specific points as I go from left to right? And then eventually I'm going off to infinity. And then you address each situation as it pops up. Next couple of examples. The first one, this limit as x approaches infinity of sine x. Again, you have to be careful with the idea of infinity as x approaches infinity. Now, this goes back to your basic trig. What does the graph of the sine function look like? Remember, it does that. We talked about that in the last section. We talked about the range of the sine function is -1 to 1. So the graph of the sine function, and it's going to do the same as you go this way. And the same is true for cosine, right? They basically look the same. But those two graphs are always oscillating between -1 and 1. I gave you the example earlier of an oscillating graph that was getting closer and closer and closer to a horizontal line, right? We talked about something doing like this. And we said the limit there would exist. But for the sine function, the limit does not exist because it just keeps bouncing back and forth between -1 and 1. It never approaches or gets closer to a single value like this one is doing, okay? So that's a straight observation. The limit as x approaches infinity of sine x does not exist. The same thing would be true for cosine. Okay. The next one, kind of similar to what we had talked about earlier where we had that e to the opposite of x. If I look at the limit as x approaches negative infinity of e to the x, right? If you look at the graph of this function, the graph of e to the x looks like this. One of our basic exponential functions with a positive base, or base greater than 1, I should say. Then as x approaches negative infinity, right, the graph is approaching 0. You could also think of it this way. If this exponent is getting large negative, then we could think of our reciprocal again. If I have a large negative exponent, then I could write that as 1 over e to the opposite of x. But since x is getting large negative, then the opposite of x is getting large positive. And now we're back to that idea that the denominator is getting large positive, so the fraction is approaching 0. Okay? So just a couple of different ways to look at that one. And then lastly in this section, so we had our infinite limits, where the limit as x approaches a of f of x equals infinity or negative infinity. We have our limits of infinity, limits at infinity. Right? The limit as x approaches positive or negative infinity being equal to some number. Well, let's put the two together. Here's an infinite limit of infinity, right? Where the limit as x approaches either positive or negative infinity is itself positive or negative infinity, right? So we're plugging in larger and larger values for x, and we're getting larger and larger values of the function, whether they're positive or negative. So here's again where you have to be careful about the idea of infinity. So for example, if I look at the limit as x approaches negative infinity of x cubed, all right, and I'm just doing this by observation, if I just plug in larger and larger values for x negative, larger and larger negative values, and I cube it, then I'm just going to get larger negative values. Right? So I'm not, and I'm going to write this, and from time to time we write things, just kind of be careful in your interpretation, right? Because that is absolutely an incorrect statement to write because, like we said, infinity is not a number. But the idea is if I plug in larger and larger negative values and I cube them, what happens to those values? Right? They're just going to continue to get larger and larger negative. So you can make use of statements like that. Just please be careful and don't misinterpret what that actually means or what you mean by that. Because that comes into play in this next piece. Here's where you have to, again, be careful about infinity and treating that as a number. So here's the limit as x approaches infinity of x to the fourth minus x cubed. Right? So, okay, maybe I can apply some limit laws here. The limit of a difference is equal to the difference of limits, but that goes back to what we said earlier, though. Remember, we said those limit laws only apply, I can only guarantee you that they're true, if the limit exists. So if the limit as x approaches infinity of our function actually approaches a number, then yeah, I can use the limit laws and say the limit of a difference is equal to the difference of the limits. But that's not the case here, because if I break this up and try to use the limit laws, it's okay, well, let's look at the limit as x approaches infinity of x to the fourth, limit as x approaches infinity of x cubed. Well, each one of those is going to approach infinity, right? I mean, this is going to approach infinity. Larger x values to the fourth power are just going to get larger. Larger x powers cubed are just going to get larger. So both of those are going to approach infinity. Does that mean I can then say that infinity minus infinity is 0? Absolutely not, right? Because infinity is not a number. Just because I'm using the same symbol doesn't mean I'm representing the same number. This is not necessarily true. Now, maybe it is in a specific case where both sides of those are approaching infinity at exactly the same rate. Then I'm always getting the same value every time I plug in the same value for x. That it could happen, but typically not. And you think about it, x to the fourth, when you plug in, if you were to plug in the same value in place of x in both cases, and you raise it to the fourth power versus raising it to the third power, x to the fourth is always going to be bigger than x cubed. Now, not only that, the difference between the two is actually getting larger as you increase the value of x. So that's a case where, look, the limit laws can mislead you if you try to treat infinity like a number, because each of those limits, I agree, is infinity, but that does not mean infinity minus infinity is 0. So that's why I keep saying be careful with infinity. Don't treat it as a number. All right, so I can't necessarily make that statement to be true. So that doesn't work. So then we say, okay, well, let's see if there's some other way that I could rewrite this thing to give me an idea of what may be happening to it. So let's try rewriting it as a product. In this case, I factored out the x cubed, right? I get x to the fourth minus x cubed. So I just factored out x cubed, and I rewrote it as x cubed times x minus 1. And then we say, okay, well, let's try the product rule. Maybe this works. So here's the limit as x approaches infinity of x cubed, which again is going to approach infinity, right? I pick a larger and larger number and cube it. It's going to get larger. Same thing is true here, though, as well, right? If I take a larger and larger value for x and plug it in to x minus 1, it's just going to get larger and larger, right? So it's infinity minus 1, which is still infinity. It's going to get larger and larger. So I can still also say that that second limit is also infinity. Now here there's no confusion, because if I take a large positive number and multiply it by the large positive number, then I'm going to get a large positive number. And there's no question about that. There's no doubt that that is true, right? Whereas when we say infinity minus infinity equals 0, that's probably not going to be true. We can't say that that's true necessarily. But a large positive times a large positive gives me a large positive. So the purpose behind these infinite limits of infinity, the main thing is with these, you've got to be careful in terms of how you treat infinity and how you, quote unquote, do calculations with infinity, or at least the concept of infinity, because you can mislead yourself sometimes with this. Okay? We're going to see some things with that pop up as we move along, and so we'll maybe have to readdress those types of issues. Okay? So you'll have a couple of problems in your homework where that's going to come into play. So your trick is, can I put this into a form that I can actually do the calculation and make a straightforward, clear observation as far as what the value of that limit is going to do. Okay. All right, that's it for that section.